Welcome back. This is a BitLearn series on modern operating system design. This is not about using an operating system. We're going to look more into how a system is designed. We'll look at some of the abstractions, trade-offs. So this will help you understand why an operating system is designed the way it is today. So if you're into academics or if you're studying computer science, this is the episode for you. So let's jump into episode number 2. So let's look into how should an operating system be organized. So when you open an application on your computer or phone, you rarely think about the operating system beneath it. You just click, swipe, tap, and things happen. You can open up Windows, you open up a browser, you start reading something, music, all of these things. But behind all this apparent simplicity lies one of the most important decisions in computer science. How should an operating system be organized? This is not about organizing data. It is more about how do you organize the different pieces of code that serve different functions in an operating system. Do you put it all together as a single monolithic block of code, or do you have a set of cooperating services? We'll look into all those design choices in this episode. So let's look at the nature of structure. So every operating system performs roughly the same set of tasks. It manages processes, it allocates memory, communicates with hardware, handles files. It does all the usual things that any operating system has to do. So there is no choice there. The operating system has to perform these functions. But what is a choice is how these responsibilities are placed. So should everything live in one powerful core? So if you take an example of the older operating systems, earliest Windows, or I can't say Unix, but yeah, definitely Windows, there was one big monolithic piece of code that was the operating system. So should responsibilities be divided into neat layers, or should we have little services that all work with a small kernel that does the core functions? So there are a lot of choices. So that is a choice that is available to operating system design. But the functions themselves, they are not choices. Any operating system has to deal with memory, has to allocate space, has to manage data, all of these things. So let's look at what these choices are in terms of design. So the first one we're going to talk about is monolithic kernels, where power is kind of centralized in one area. The earliest and the most straightforward answer to the structure question was the monolithic kernel. So in a monolithic design, all operating system services run inside a single kernel address space. Think of it like a very large program where the programmer has taken the responsibility of separating out functions, but it all still runs as one big large program. Device drivers, file systems, process scheduling, everything is very tightly integrated. There is an advantage with this approach. The advantage is, since all of them are working within a single process space, it's much faster. They're very much tightly integrated with each other, so the performance is going to be pretty good, and system is conceptually simple. But there are few boundaries that are difficult to cross, so we'll talk about that. So but all of this comes at a certain cost. Everything runs with full kernel privileges. So if you look at a CPU, the way CPUs are designed is they allow you to run some things in a kernel mode where it has privileges to access every piece of hardware, or you can run it in user mode where the program has access to certain aspects. So generally kernel mode allows us to access any IO capabilities like a disk drive or a web camera or any of the hardware interfaces. They run as kernel privileges. Whereas if you run something as a user application or a user privileged process, that may not have access to the IO capabilities of the CPU or the overall system. So that's the difference between kernel privileges and user privileges. So a failure in any one of these pieces will bring down the entire system in a monolithic system, because everything is tightly integrated. If I fail to read data from a disk drive, my whole operating system might crash, or I might get an error which needs to be handled. So a simple buggy driver can crash the entire operating system. Debugging also becomes difficult. So the monolithic kernel kind of embodies a very strong belief. The belief is the core must be trusted completely. So whoever or a small team of people who are writing the operating system, they trust each other completely. One of them writes the device driver, somebody else writes an application that is used to, let's say, talk to the OS, maybe a shell or a GUI like Windows. So it is a design optimized for speed and simplicity. And that's how many of the early operating systems were written. I don't want to keep dropping the name of Windows, but I believe the early version of Windows 3.1 was pretty much monolithic. But but this approach kind of assumes that errors are rare and they are manageable. It is basically a system of trust. Each developer trusts the other person to not bring down the system. So it's simple, it's much faster, but it relies on people trusting each other and people being at the same level of, let's say, technical skill set in terms of managing issues and design decisions. So it's it's good for a small team or one or two people doing things. But as we start writing more and more complex operating system, we need to start putting some layers of responsibility. So this is the approach called layered systems, where as the systems grew more complex, designers kind of began to seek more order in the structure. In a layered design, the OS is organized into a hierarchical level. Each layer provides services to the layer above it and relies only on the layer below it. So it's like saying, if I have the CPU at the base, the hardware is at the bottom, we have one layer which talks to the hardware, which is the smallest kernel or a small layer which talks to the interfaces, and then we have another layer on top of that which allows us to do system calls, which allows us to use this hardware, but the applications themselves which talk through the system calls, they are protected from the hardware. So we are basically talking of a simple 3-layer approach. We have user, we have the system calls, and then we have the actual hardware drivers. So this approach kind of improves clarity. Each layer has defined responsibilities. The system becomes easier to reason, easier to document, easier to teach, and bugs can be traced very easily to specific layers. However, layers introduce overheads. Requests must pass through multiple boundaries, performance can suffer. So in practice, real-world systems often bypass the layer to regain speed. So when I am the person who understands the OS very well, if I want to write something that is very quick, efficient, I would probably write something at the lowest level and have direct access to the hardware. So you can't really restrict developers from building something at the bottommost layer. So the layered system reflects a very different belief. The belief here is correctness and clarity are worth some loss in efficiency. There are layers, there is an overhead in passing information from the topmost layer to the bottom, but it comes at the it comes with a cost of efficiency, loss of efficiency, but it gives us a lot more correctness and clarity. But it is much more disciplined over just pure raw performance. Now we get into the modern approaches of kernels and microkernels. So let's get into the next approach, which is microkernels. So here the philosophy is about minimizing trust. So the microkernel approach takes separation to its logical extreme. So in a microkernel design, the kernel is deliberately kept small. It's like a very small piece of tightly integrated code that runs on the CPU and which has access to most of the hardware functions. Only the most essential mechanisms remain inside the kernel. Typically, it manages scheduling, basic memory management, IPC, inter-process communication, and access to the hardware. And everything else like device drivers, file system, all of these things, they run in user space as independent services. They talk to the kernel to get the job done. So if the kernel is the one that's doing the actual, let's say, hardware interface to connect to the webcam, so how does the device driver work? It switches into kernel mode. So the kernel gives it special abilities to run in kernel mode, use the web camera interface, get data out of that, and then switch back into user mode. So it's up to the designers to design how long they want to stay in kernel mode. So we'll talk about why kernel mode is so important and why it helps us in designing good operating systems. So this kind of dramatically changes the system behavior. If a driver crashes, the operating system does not crash. The services can be restarted independently, fault isolation improves, security boundaries become stronger. But microkernels introduce new challenges. The communication between components now happens through message passing. So there is a device driver to a webcam and there is a mic that I am using here. This uses another device driver. Both of them have to communicate with each other to create the final video. So how do they work? Each of these drivers, they have to switch into kernel mode, connect to the camera, get the video image, and then switch back. and now the mic that I'm using, that uses its driver to switch to kernel mode, get its audio data and switch back. So it's a lot of communication between these processes that have to come together to create the final video. I just gave a simple example, but that kind of conveys the idea of how communication becomes more important in microkernels. So still the philosophy behind microkernels is pretty simple. Bugs are inevitable. My mic driver could fail, which means audio goes, or my camera driver could fail, which means video goes. It doesn't mean that the whole video is done, dead. I may still be getting one of them. So I'm just using a very simplified example. You could take a communications link, or you could take a modem or a router or Wi-Fi chipset, whatever. So this approach treats failure as not an exception, but as a normal condition that has to be managed. And then we have hybrid kernels. As we went through all these different approaches, in practice most operating systems settle somewhere in between these approaches. So some things are monolithic, some things are microkernel approach. So hybrid kernel borrows ideas from microkernels. It gives us modularity, isolation, but it keeps the performance critical components inside the kernel. So they acknowledge that some of the elegance of keeping something minimal accepts the practical demands of real world systems. So hybrid designs are not philosophically pure. They are complex, sometimes inconsistent. Sometimes I, as the designer of the entire operating system, I might say something runs as a small monolithic block and I want to keep everything out there. Some things I might split a little more into services, kernel mode functions, all of these things. So the hybrid approach carries a kind of an unspoken admission. Ideas are very valuable, academically they sound great, but systems must survive reality. So with that, I think we looked at some of the high level approaches used to design an operating system. So we will get more and more into details of the OS design itself in the coming episodes, but this should give you a base to understand what kind of a philosophy the OS designers have taken. If you're looking at Linux, you can figure out which approach they're using. If you're using Windows, you can figure out the approach, Mac OS, FreeBSD, all of them. So structure as a philosophy is at the core of operating systems. It is not a technical tweak or something. It's the idea of how we structure our operating system to perform is a belief in a certain design. So do you trust the core or do you limit it? Do you kind of prioritize speed or resilience? Once you choose a structure or a design, this shapes everything that follows. Because we have chosen a microkernel approach, we need to rely more on security models because there are so many processes communicating with each other. Because we chose a monolithic approach, security is now restricted to a small core team of people or one person who builds the monolithic kernel, so he can decide what works. So debugging difficulty also goes up because if the small team disappears or if that one person disappears, the monolithic core is very hard to debug because the ideas are gone. So these decisions are kind of very difficult to reverse. So once you take an approach and start building the OS, there is no going back. It's going to be pretty expensive to rewrite the kernels. It's possible, kernels can be rewritten, but it comes at a very heavy cost. So this structure hardens our architectural decisions and becomes kind of the destiny of the operating system. The same structural questions appear everywhere in software. Monolith versus microservices, tight coupling versus loose contracts, centralized versus distributed, all of these things. But operating systems simply face these questions much earlier. Even before we talk about enterprise architecture or scalable systems or web development, all of those things, operating systems have to make a decision on how they structure these things much earlier. And it is at a scale where consequences are impossible to ignore. So if the operating system, which is so core to running everything else around it, if it makes a certain choice, that kind of has a consequence for everybody else in the system. That is how important it is. So I hope you understand what the philosophy of design and architecture is for an operating system, and we looked at a couple of those variations. We will start focusing more specifically on the functions of an operating system as we go ahead. We'll start looking at processes, threads, how do we create this illusion of everything seeming to work seamlessly in the coming episodes. So if you have enjoyed watching, do subscribe, do like, put some comments down below. Let me know what you want to hear. Let me know how I can improve what I'm talking about, because I do have a lot of information in my head and I'd be glad to get some feedback on how better I can send it across to you. So thank you for watching and keep learning.